When airspace is breached, response times are measured in seconds. You do not have time to second-guess what your radar is showing you. In March 2023, India's Ministry of Defense authorized a 2,800 crore contract for a new class of ground-based surveillance to secure its skies. The hardware at the center of that acquisition is the Arudhra medium-power radar. It is built to lock onto targets across a massive 400-kilometer detection range. While the range provides the necessary reach, the underlying architecture provides the speed. Arudhra operates as a 4D multifunction phased array system. Deploying this system solves an immediate tactical problem on a volatile border, while simultaneously proving the viability of India's domestic defense manufacturing sector. Securing India's northern and northeastern airspace presents a strict physics problem. Deep, winding mountain valleys instantly break the line of sight required for traditional tracking. Unlike scanning across flat desert terrain, firing radar into jagged vertical geography creates dangerous blind spots, or radar shadows, where targets can easily hide. Mastering this specific airspace requires stripping away the mechanical, slowly spinning radar dishes of the past and adopting electronic phase steering. We are going to deconstruct the exact physics of that electronic steering, map its integration with automated software, plot its deployment across the Himalayas, and examine the macroeconomic impact of building it domestically. Understanding the microphysics inside the radar panel exposes the massive scale of its geopolitical value. First, we have to define 4D tracking. A standard system plots distance and compass direction. A 4D architecture calculates range, azimuth, elevation, and the target's exact velocity over time. Legacy radars rely on physical motors to spin a massive dish. That physical limitation means they only update a target's position once every few seconds when the rotation is finally complete. A phased array architecture bypasses those physical motors entirely. The flat face of the Arudhra is actually a dense grid of thousands of individual transceiver modules. These individual modules emit overlapping electromagnetic waveforms simultaneously. By precisely manipulating the timing, or shifting the phase, of the signals emitted across the grid, the radar creates a combined wavefront that angles in a specific direction. This phase shifting lets the combined radar beam instantly jump horizontally to track azimuth, without the physical panel moving a single millimeter. It controls elevation the exact same way, snapping vertically in fractions of a second. A physical dish takes seconds to sweep the sky. Electronic steering repositions the beam in microseconds. When tracking a supersonic aircraft performing aggressive maneuvers, a 3-second mechanical delay means you lose the target entirely. Instantaneous repositioning is mandatory. The static exterior of the Arudhra is an illusion. It is thousands of independent, microscopic radars working in perfectly timed unison. Raw physical detection creates its own data problem. In congested airspace, seeing an object on a screen provides no context. Operators must determine intent immediately. That requires a cognition layer, managed by the Arudhra's co-located identification friend or foe, or IFF, system. The operational sequence works like this. The primary phased array beam hits an unknown aircraft and registers its location. Instantly, the IFF system fires a specialized interrogating secondary beam straight at those exact coordinates. If the aircraft is an ally, its onboard transponder automatically returns a cryptographic signal, confirming its friendly status. This automated split-second classification removes human ambiguity, preventing friendly fire in dense operational theaters where military and civilian traffic mix. The phased array hardware acts as the physical eyes of the military, and the IFF software acts as the cognitive processor assessing the threat. After successfully passing field trials with the Indian Air Force, these theoretical specs are now confronting physical geography. The military is prioritizing deployment in the highly sensitive sectors of Jammu and Kashmir and the Northeast. Projecting a 400-kilometer surveillance dome from these high-altitude positions covers a massive expanse of remote territory. But the true advantage is the instantaneous elevation control, allowing the beam to penetrate deep into glacial valleys before instantly jumping to scan the highest peaks. That combination of sheer range and highly agile electronic steering eliminates the topographical blind spots that hostile aircraft use to mask their approach. The Arudra's specific architecture was purpose-built to conquer the extreme vertical realities of the Himalayas, sealing the airspace into an unbroken surveillance frontier. Dominating that airspace required building an entirely new industrial supply chain to produce the radar. This hardware acquisition is driven directly by the Aatmanirbhar Bharat, or Self-Reliant India initiative. The government routed this procurement through the strictly defined Buy Indian IDDMM category, indigenously designed, developed, and manufactured. The pipeline starts with domestic engineering, relying on core designs generated by the DRDO. Those blueprints flow directly to Bharat Electronics Limited for large-scale manufacturing. Executing this massive contract forces the lead manufacturer to source components from hundreds of smaller domestic enterprises across the country. Of the 3,700 crore rupees allocated for Air Force upgrades, the Arudhra radar ecosystem alone accounts for over 2,800 crore rupees. That capital injection forces a structural pivot. It shifts the local industrial base away from importing foreign tech and scales up sovereign manufacturing. The remaining 950 crore rupees of that total contract actively funds 129 DR-118 radar warning receivers to upgrade the Sukhoi Su-30 MKI fighter fleet. Pairing advanced airborne electronic warfare upgrades with powerful ground-based radar systems builds a highly resilient, multi-layered defense network. Every rupee spent acts as a catalyst, expanding the heavy industrial capacity needed to build complex systems at scale. The successful design, testing, and deployment of Arudhra proves that domestic Indian engineering can meet the world's most rigorous military specifications. Securing the physical airspace over the Himalayas is the immediate tactical result. The long-term outcome is securing the sovereign future of India's defense industry.